Hello dear students, welcome to my YouTube channel Mr. Physics. I am Mahesh Naravoli, an educator by passion and choice, having 15 years of experience and have privilege of guiding more than 15,000 students. I am here to make physics simple, clear and powerful for you. In today's video, we are going to discuss about resistors in series and parallel and their respective key points or shortcuts for competitive exams. So let us begin with our first topic, that is resistors in series. Resistors in series. A resistor is a device which provides a known value of resistance. Here, resistors are said to be connected in series if they are connected end to end, and they are connected across a battery. Let us consider R1, R2 and R3 are three resistors connected in series across a battery of providing a potential difference of V. From plus to minus, there is flow of current of I. So here we have some conditions of series combination. In those conditions, the first condition is the resistors are connected end to end. The number of resistors are said to be connected in series if they are connected end to end. To explain more about the series combination, I am taking an equivalent circuit which is consisting of an equivalent resistor, that is Rs. An equivalent resistor is the one which gives the same amount of resistance as that of combination of resistors. Here whatever resistors we have, R1, R2, R3, all these three together, whatever resistance value they give, that is given by a single resistor Rs. And the second condition of series combination is the amount of current that is flowing in the circuit is always a constant, because there is no branching phenomenon in any of the part of the circuit. Hence the current remains constant, and potential difference across the combination is equal to sum of potential difference across individual resistors, that is V equal to V1 plus V2 plus V3. So altogether, the first paragraph of the explanation of the circuit is number of resistors are said to be connected in series if they are connected end to end, such that the current flowing across the combination is constant and the potential difference across the combination is equal to sum of potential difference across individual resistors. To prove the relation between equivalent resistors and individual resistor, we are going to use the Ohm's law. Using Ohm's law, we apply Ohm's law for individual resistors as well as equivalent resistor. So initially for individual resistors I am applying. So for individual resistors, initially the general formula of Ohm's law is V equal to IR. So let us see the individual resistors. See there, whatever V1, V2, V3 are there, these are the potential across individual resistors. So we should observe this part of the circuit. This is one resistor. So V1, R1 and the current is I. So V1, R1, current is I is a constant. And similarly we can write for the second resistor also as V2 equal to IR2 and V3 equal to IR3. Similarly for effective resistor, what equation we can write? That is V equal to IRS. You can observe in the circuit the potential is V, current is I and the resistance is Rs, hence I can write as V equal to IRS. Now we should equate all these values, in equation 1. Equation V1 we have V equal to V1 plus V2 plus V3, we have it here. In place of V I will write IRS in place of V1, IR1 in place of V2, IR2 in place of V3, IR3. So I'll repeat the term IRS here, and in the right hand side I'll take R common, and the remaining terms are R1 plus R2 plus R3, and here this I will cancel. Therefore we get the term that is Rs is equal to R1 plus R2 plus R3. So this is the relation between equivalent resistance and individual resistances connected in series combination. Or the same equation I can write in the summation form as Rs is equal to summation of Ri, where I lies between 1 to n. Like for two resistors, if there are two resistors, then equation becomes Rs equal to R1 plus R2. If there are four resistors, Rs equal to R1 plus R2 plus R3 plus R4. So overall, to calculate the effective resistance, we need to add the values. The same thing we can write it in sentence formation as in series combination, the effective resistance is equal to sum of individual resistances. In series combination, the effective resistance is equal to sum of individual resistances. This is the last conclusion of series combination. So Rs is equal to R1 plus R2 plus R3 for 3 resistors. For n resistors, similarly we can say that Res is equal to R1 plus R2 plus up to n resistors having value Rn. So this is the relation between effective resistance and individual resistances. For more explanation about series combination, I am taking few note points here which are very essential to solve any kind of circuit, whether it is series or mixed grouping. We are going to use the rules to find the values. So initially in the note point, I am taking the first note point where 3 resistors, that is 1 ohm, 2 ohm, 3 ohm are in series. Then immediately for Rs we will calculate, that is 1 plus 2 plus 3, that becomes 6 ohm. So you can observe in this combination 3 ohm is the highest value, and the value of Rs is greater than the highest value of resistor in the combination. So therefore we say that the effective value, the effective resistance in series combination is greater than the highest one from the combination. So what is the sentence? The effective value of resistance in series combination is always greater than the highest one from the combination. Second point we have, that is for two equal resistances in series. So what is this two equal resistances in series? So let us take two equal resistances and potential, that is a battery plus minus. Let us assume that these two are equal. Remember, initially in the derivation I said you, that is when the resistors are equal, the potential get distributed equally among those two resistors, and whatever the current is flowing is always a constant, and effective value will be R plus R, that is 2R. Effective value will be double of individual value, that is example 2 ohm 2 ohm series, answer is double 4 ohm. You can just add also, not an issue, but it's just a small trick. Similarly, we have third point, very important key point over here, that is for n identical resistors, each of resistance R. Identical. What is identical? Identical means the resistors having same value of resistances. So here Rs is equal to R plus R plus R. Similarly, n number are there. Therefore, Rs will be equal to n into R. For this, I will take an example, that is 1000 resistors each of 3 ohm resistance are in series. Observe carefully. 1000 resistors. What is this 1000? This 1000 is N. Each of resistance 3 ohm is R. They are in series. Therefore, Rs equal to N into R. N is 1000. Each value is 3. The effective value will be 3000 ohm. So, lengthy of the lengthiest question also can be solved using these tricks. So, same way, we have one more important factor to be explained, that is why do we go for series combination? Very important point. Why do we opt or select, why do we go for series combination? Imagine we have few resistance values like 2 ohm, 3 ohm, 6 ohm like this, and we are in need of 10 ohm. So whenever our requirement is high compared to the available resistances, we go for series combination. So series combination is done. Series combination is done to get higher value of effective resistance from lower value of resistances available. So compared to the available resistances, if your requirement is more than that, then we go for series combination. One more important point, we have equation V equal to IR, and we know that I is constant, Therefore V is proportional to I. V is proportional to R. Sorry, V is proportional to R. So when V is proportional to R, higher the resistance, higher the potential. Like V1 proportional to R1, V2 proportional to R2. So similarly we can write as V1 by R1 equal to V1 by R1 equal to V2 by R2. So this is key point related to the series combination where I is constant and higher the resistance, higher the potential will be required for the resistor. So one more, just within few minutes we are just going to do the brush up. So as I told you, the series combination conditions, that is connected end to end, and the current flowing is constant. Potential difference across combination is equal to sum of potential across individual resistors. Using Ohm's law we wrote the equations, that is V1 equal to IR1, V2 equal to IR2, V3 equal to IR3, and for effective V equal to IRS. So all these when we equated, we got the relation RS equal to R1 plus R2 plus R3, and in series combination the effective resistance is equal to sum of individual resistances, and the effective value is always greater than the highest one from the combination. When two equal resistors are in series, the effective is double of it, and the potential difference get distributed equally among those two. For n identical resistors, each of resistance R, Rs equal to R1 plus R2 plus R3. Similarly, we write as R plus R plus R up to n number. And for that I have taken an example. 1000 resistors, each of 3 ohm resistance are in series. So we got the answer. Why do we go for series combination? And what are the conditions for V and R with respect to keeping chi as constant? So this is all about series combination explanation. Further, we are moving to the next part of today's video, that is resistors in parallel. So here in parallel combination, the rule is the number of resistors are said to be connected in parallel if every end of each resistor is connected to same common point, and these are those common points. Now any point we can take left and right as common point. So here we have taken 3 resistors, and the resistors are R1, R2, R3 connected in parallel across a potential difference of V. In the direction of plus to minus, there is flow of the current, and as there is branching process from this point, the current distributes into 3 parts as I1, I2, I3. I1 is flowing across R1, I2 is flowing through R2, and I3 is flowing through R3. And we have already told that higher the resistance, lower the current. Hence, wherever if R1 is greater than compared to other, then the value of I1 will be less. We'll discuss about this immediately. And for this we take an equivalent circuit, and that equivalent circuit consists of a single resistor, and the name of that single resistor we will take it as RP. So as usual, conditions for this, for just like how we derived for series combination, conditions, first one is every end is connected to same common point. Every end is connected to same common point. Second condition is V is a constant. Not only in this, for any electrical circuit for parallel combination, the potential difference will be always a constant. And the third important point, current flowing through the combination is equal to sum of current through individual resistors. Just like main current is equal to sum of branch currents. Here the main current is I, is getting branched here into I1, I2, I3, and these sum of I1, I2, I3 will be this main current I. Hence we write the statement as I equal to I1 plus I2 plus I3, which is nothing but main current is equal to sum of branch currents. As usual, we will use Ohm's law. Using Ohm's law, we will write the expressions for individual resistances or individual resistors. That is V equal to IR is our formula. For individual, you just see here, V is constant for all. Current is I1, resistor is R1. So I1, R1. Therefore, I can also write as I1 equal to V by R1. Why did I write in the form of I1? Because I need to equate that in the equation number 3. That is I1, I2, I3. Hence, I have written it in the form I1 equal to V by R1. Similarly, I can write for I2. Yes, I2 equal to V by R2 and I3 equal to V by R3. Similarly, we can take for effective resistance or effective resistor. For effective resistor, V equal to IR form, V equal to IRP. Therefore, I equal to V by RP. So, equate all these in equation 1. In the next step, equate all these in equation 1. So, what is I? I equal to V by RP. What is I1? It is V by R1. I2 is V by R2. I3 is V by R3. I'll take V common here. V by Rp equal to V is taking common 1 by R1 plus 1 by R2 plus 1 by R3. V will cancel. Therefore, we get the expression as 1 by Rp equal to 1 by R1 plus 1 by R2 plus 1 by R3, or I can write in the summation form as 1 by Rp is equal to summation of 1 by Ri, where I lies between 1 to n, and this expression 1 by Rp is the required expression. The same thing we can write in the sentence form as in a parallel combination, the reciprocal of effective resistance is equal to sum of reciprocals of individual resistances. In parallel combination, the reciprocal of effective resistance is equal to sum of reciprocals of individual resistances. That is 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. In parallel combination, the reciprocal of effective resistance is equal to sum of reciprocals of individual resistances. If there are only two, we can write as 1 by Rp equal to 1 by R1 plus 1 by R2. How many ever are there, we have to write so many resistance values. So related to this, we are going to take the note points or key points. Observe carefully. So initially I'll take for 3 resistors as usual, like how we have taken for series combination. 1 2 3 same values I'll take here also. Okay, so that is 1 ohm, 2 ohm, 3 ohm are in parallel. Hence we get equation as 1 by Rp equal to 1 by R1 plus 1 by R2 plus 1 by R3. So here 6 is the LCM, into 6 into 3 into 2 will get as 6 plus 3 plus 2. Remember LHS it is 1 by Rp, and this will be equal to 11 by 6. Therefore Rp is equal to 6 by 11. Therefore we get the value, that is Rp is equal to, we get the value that is Rp is equal to, after calculating, around 0.54 something will get. So you can observe here the value of Rp is lesser than 1 ohm. This 1 ohm is the least one in the combination. So hence we can say that Rp is lesser than the least one from the combination. That is effective resistance in parallel combination is always lesser than the least one from the combination. Example, if we have 1 ohm, 100 ohm, 200 ohm in parallel, then remember Rp will be less than 1 ohm. So this is a trick to identify the answer within seconds. Similarly, for 2 resistors we can take one shortcut. For 2 resistances in parallel, that is 1 by Rp equal to 1 by R1 plus 1 by R2, which is equal to R1 into R2 is the LCM. Here I'll multiply and write R2 plus R1. Therefore if we take, we get it as Rp equal to R1 into R2 divided by R1 plus R2. Generally while solving we forget taking reciprocal. For that we can make it this as a shortcut for 2 resistors only. This formula can be used only for 2 resistors. If those 2 resistors are equal, for 2 equal resistors or 2 equal resistances in parallel, kindly note this is an important condition. If there are two equal resistors, that is R and R, the current flowing will be I. Here when it get distributed, it distributes as I by 2 equally, because the resistances are equal, and as usual the potential V will be constant or same. And for these condition we can write, that is Rp equal to R1 into R2 divided by R1 plus R2. R1 into R2 will be R square by 2R. 1 R will cancel. Therefore Rp we get it as R by 2, half of the individual value. When 2 equal resistors are connected in parallel, they will be half of the individual value. Example we can take, that is 4 ohm in parallel, Rp will be 2 ohm. Very simple, within fraction of second you will get the answer, because it is half of the individual value. Similarly we can take one example for this. that is whatever we have discussed here. For this I'll take an example. One more example we'll discuss in the form of a circuit. If you have a circuit like this, and the values of the resistors are like 2 ohm 2 ohm each, R equal to 2 ohm, and this R is equal to 2 ohm. If the current flowing here is 2 ampere, how much it will flow here? It will be 1 ampere, and here also it will be 1 ampere, and in this case Rp equal to 2 by 2, that is 1 ohm. Very simple concept. Effective value is half of the individual value. Similarly, fourth important key point here, that is for n identical resistances, each of resistance R, that is 1 by Rp equal to 1 by R plus 1 by R up to n number, that will become n by R, and remember this is 1 by Rp, therefore only Rp will become R by n. And whatever example we took for series, same example we'll take here, that is 1000 resistors, each of 3 ohm are in parallel, therefore we get Rp equal to, this is n, this is R, okay, therefore Rp is equal to R by n. R is 3, n is 1000, that is 0.003 ohm. So here we are finding effective resistance again. And in the next step, very important, why do we go for series parallel combination? As we have figured out just now, in all the cases, see in the first example itself, the value of effective was lesser than the least one from the combination. Similarly, we do this parallel combination to get the least value or lesser value of effective resistance, to get lesser value of effective resistances from higher value of resistances available. Example, see, I'm having 1 ohm, 10 ohm, 20 ohm, 100 ohm, 50 ohm like this. If I want the resistance value to be less than 1, I should include 1 ohm in the parallel combination. So the sentence says the parallel combination is done to get the lesser value of effective resistance from higher value of resistances available. Similarly, one more important point, I equal to V by R we are having. V equal to constant here, so therefore I can write as I is inversely proportional to R. Hence we say higher value of resistance implies lower value of current. Higher the resistance, lower the current. Based on this, we can even discuss the distribution of the current using this concept itself. That is, imagine a circuit which is having the branching phenomenon. Imagine here there is a flow of 6 ampere current. R1 value is 6 ohm, and similarly R2 value is 3 ohm. So it get distributed here into parts such that the current is in ratio 1:2. So 1 will flow in the higher resistance value, 2 ratio will flow in the lower resistance value. Thus 6 will be divided into 2 and 4, which are in the ratio 1:2. 2 ampere will flow here, which is having higher resistance, and 4 ampere will flow here, which is having a lower resistance. Higher the resistance, lower the current. Based on this phenomenon, this 6 ampere is distributed into 2 and 4, which are in the ratio 1:2, because the resistance ratio are in the ratio 1:2 again. Higher the resistance, lower the current, lower the resistance, higher the current. And to cross check, the sum of the branch currents will be equal to the main current. That is also proved here. And one more example we are discussing, that is second example. Kindly observe carefully and you comment your answers here. Solve this and comment your answers here, and let me know whether you have followed the concept or no. So this is 36 ampere is flowing. The resistance value is 1 ohm and 8 ohm. What are the values of I1 and I2? So if you have understood the video, kindly comment your answers as what are the values of I1 and I2 with the reason, and observe the resistance values here. It is 1 ohm and 8 ohm. The value of the main current that is flowing is 36 ampere. Comment your answers below. And if you have understood the video, if you have liked the content, kindly share among your friends. Kindly support the video by giving more response towards in the comment section. Thank you one and all.